Hello and welcome to lecture 36 of the course Theory of Computation. In lecture 35, we started building towards the theory of undecidable languages. We defined bijection, it's called a correspondence in CIPSR. We defined countable numbers, countable sets. We saw that n, q, set of all natural numbers, set of all integers, set of all rational numbers are countable. We saw that R, the set of all real numbers, are uncountable. Right. Now we'll see further. We'll move further ahead. Right. We'll see more sets that are countable and uncountable. Right. And as we build towards the theory of undecidable languages. Right. Okay. So just like we saw R by using this diagonalization argument, we'll see another set which is uncountable, right? So let set B be the set of all infinite binary strings. Okay, binary strings, infinitely long binary strings. So I mean strings like 0, 1, 1, 0, something, right? So each element in this set is an infinite binary string, right? So B is a set of all infinite binary strings. So not finite binary strings. So if, for instance, 0, 0 or 1 or 1, 1, 0, 1, these strings are not there in B, right? So the elements of B are infinitely long binary strings, right? So this B is uncountable. Why is that? We can pretty much use the same argument, the diagonalization argument used in the uncountability of R, right? So suppose suppose it is indeed countable, right? So which means there is a listing of the elements of B, right? So let's say the first number in the listing was 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, something. Second number in the listing was 1, 0, 1, 1, 1, 0, 1, 0, 0, 1. Third number was 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, right? Fourth number is 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, right? Something like this, right? Suppose there is some listing that is available, or some ordering that is possible of all the numbers in B, right? So not numbers in B, all the elements of B. So each element is a infinitely long binary string. Now just like in the uncountability of R, we produce an X which does not feature in the listing. Here also we can use the same technique to produce such an X. So look at the first element or first bit of the first string, which is 0. Second bit of the second string, 0. Third bit of the third string, 1. Fourth bit of the fourth string is 0. So it is 0, 0, 1, 0. So I take the opposite. So I define X to be 1, 1, 0, 1 and so on. So if the fifth bit of the fifth number was, let's say, 1, then the fifth bit of X would be 0, right? So I choose X in such a way that the fifth bit of X or the ith bit of X differs from the ith bit of the ith string in this listing, right? So X is chosen such that ith bit of X is not equal to ith bit of ith string in the listing. The rest the rest is same as in the uncountability of R. So this means that X is different from all the numbers in the listing. So let's say X is different from the 50th string in the listing, because the 50th bit of X is different from the 50th bit of the 50th string in the listing, and so on for 100 string or 200 string and so on. So X is different from all the strings in the listing, which means the listing was not proper to begin with. How come X is different from all of them? That means X does not get captured at all, which means that the listing is missing numbers, right? So, for instance, X is such a number. So, this means the set B of all infinitely long binary strings, this set is uncountable, right? So, the set of all infinite binary strings is uncountable. Now, let us see another set which is countable. Right? So, consider a finite sigma. So, all the alphabets that we have seen many languages like while seeing DFAs, NFAs, Turing machines, etc. All of these languages were built on some alphabet, right? So, it could be binary alphabet, it could be English alphabet, it could be decimal alphabet. All of these were finite. So, let us take a finite sigma, finite alphabet. Then the set of all strings, right? So, given any finite sigma, the set of strings will be infinite, right? The set of all, like you could have, because you could have infinitely long strings also, right? Or you could have finite strings, but of infinitely many possible lengths. So, this theorem says that the set of all strings is countable, not uncountable, countable. So, this I will not. It's easy to just give the listing, right? So, suppose sigma is AB, right? AB, right? It's binary, but not 0 1, but AB. So, the listing is very simple. If we first write epsilon, which is the empty string, which is a string of length 0, then write A comma B. So, A and B are strings of length 1, which is only single symbols. Then we write the 4 strings of length 2, AA, AB, BA and BB, right. Then we write the strings of length 3. So, if you think about it, there are 8 of them, AAA, AAB, ABA and so on up to BBB. Then we write strings of length 4, then we write strings of length 5 and so on. So, it should be evident that all the possible strings are captured in this listing. So, if you ask me some long string A, B, 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 A or something, then although it may be difficult, but I can tell you that this string will appear as number, let us say 526 in this listing, right? Some number. So, I don't know, I did not calculate it, but it should be possible to tell where that number appears, where that string appears. So, in other words, every string is guaranteed to be captured in this listing, right. So, this listing demonstrates that sigma star is countable. So, we are just directly giving the listing itself. So, sigma star is countable. Okay. Now, given now let us move on to the next next set. So, given sigma, we talked about sigma star. Sigma star is a set of all strings. Now, let me talk about the set of all languages, over sigma. So, what is a language? A language is a subset of sigma star. So, now I am talking about set of all subsets of sigma star, right. So, L is a set of all languages over sigma. So, L is defined to be the set of all subsets of sigma star, right, because a language is merely a subset of sigma star, or in other words, the power set is the power set of. So, set of all subset is called the power set, right. So, L is a set of all languages over sigma, which is the set of all subsets of sigma star. The theorem states that for any finite sigma, the set of all languages is uncountable. So, sigma star itself is countable, the set of all strings is countable, but the set of all languages is uncountable. So, how we will show this is by defining a bijection between the set of all languages and the set B, right. Sorry. So, we showed that B, the set of all infinite binary strings, was uncountable. What we will do now is to demonstrate a bijection between the set of all languages and the set B, right. Now, B is uncountable, and if I can have a mapping or bijection between L and B, the set of all languages and B, that means this also has to be uncountable. It cannot be that L can be countable and B can be uncountable, and then we can have a bijection, right? Because that would imply that B also is countable, which you know is not the case, right? So okay, so we'll show the bijection, right? So the bijection automatically implies that since B is uncountable, it implies that L is uncountable, right? Let's see how. So let sigma star be the set of all strings of over sigma, right? Sigma star is a set of all strings over sigma. So let sigma star be represented like this: S1, S2, S3, meaning the first string, second string, third string, and so on. Okay. So notice this. So even though this may seem like a innocuous or simple notation, actually this actually carries a meaning, and this actually the fact that I can write the sigma star as the first string, comma second string, comma third string itself means that the set of strings in sigma star is countable, right? So this notation, what is it telling us? It is telling us that there is a first string, then there is a second string, then there is a third string, and so on. So it implicitly assumes that I am listing the strings of sigma star as the first string, second string, third string, which is kind of saying that the set is countable, right? So we are implicitly using the fact that it is countable. We know that sigma star is countable, so it is okay. But I am just kind of alerting you to the assumptions just inherent in this notation. Sometimes you just have a notation, and that notation itself, just because we are writing in a certain way, that itself carries an assumption with it, right? So that's what I want to kind of highlight here, right? Just the fact that I am writing it as first string, second string, third string itself assumes that sigma star is countable. We know sigma star is countable, so it's fine. This assumption is fine. But one has to be careful in general, right? So now let me define the mapping or the bijection from L to B, right? So this bijection is going to be like this. So suppose, so sigma star, let's say let's take it two symbol alphabet A and B. So let me order the elements of sigma star like here. So I have the empty string A, B, A, B, A, B. So first strings of length 0, then strings of length 1, then strings of length 2, then strings of length 3, and so on, right? So how will I map? So the point is that we are going to give a mapping from L to B, meaning for given any language, L is a set of languages, given any language, B is a set of infinite binary strings. Given any language, we are going to map it to an infinite binary string, right? So let's say we give this language. So now I can, so let A be this. So I write all the strings of length 0 in A, so which is only the empty string. Then I write all the strings of length 1. So in A is not in A, small a is not in A, but small b is in A. Then I write all the strings of length 2, which is AA and BA. AB is not in A, BB is not in A. Then I write the strings of all the strings of length 3. So AAA is not in A, perhaps the next string is in A or not. Okay, so this is how I will write the language. Now this itself gives me a binary string. So the way is this. So in the ordering of sigma star, so the first string was empty string, and A contains the empty string. So now we put the first bit to be 1 because empty string is in A. The second string in sigma star was small a, which is not there in the language A. So the second bit of the string is 0. Small b is the third number which is in A, so the third bit is 1. Fourth bit is 1 because A is in the language. Fifth bit is 0 because AB is not in the language. Sixth bit is 1. Seventh and eighth bits are 0, and so on. So now notice that this string 10110100 indicates this language A, right? So this is an infinite string. So this will extend up to infinity. So this will tell us which strings of sigma star are in A and which strings are not in A, right? So this infinitely long binary string corresponds to one language and only one language, which is A, and A corresponds to only this binary string. So this is a bijection from the set of all languages to the set of all infinite binary strings. So sometimes this kind of representation is called the characteristic string of A, right? Because I have all the strings in sigma star and I am telling which strings of sigma star are in A and which strings are not in A. Right? So 1 indicates that string is in A, 0 indicates that string is not in A. Right? So this chi, sometimes it's called chi A. So now this mapping of looking at each string, whether it is in A or not, gives us a mapping from the set of all languages to the set of all infinite binary string. So given a language, I can give you the infinite binary string. Given an infinite binary string, I can tell you which language it corresponds to. Hence, this is a bijection. This means the size of L, which is the set of all languages, and the size of B, which is the set of all infinite binary strings, is the same. This means that since B, we have already seen that B is uncountable, this implies that L is also uncountable. Right? So yeah, that's the proof that the set of all languages is uncountable. So just to recap, we showed that the set of all infinite binary strings is uncountable. For a finite alphabet, the set of all strings is countable, but the power set of all strings, which is the set of all languages, is not countable. Right? Now, this is going to be used, like the fact that the set of all languages is uncountable is going to be used to show that there are undecidable languages. Right? So, we are not going to show that a specific language is undecidable, but this will imply that languages are undecidable, there are undecidable languages. The proof is fairly simple, but it is not constructive, or in the sense that it is not directly going to tell us which language is undecidable, but it is very simple. So it is like this: suppose you have 10 mangoes and there are 12 people, right, or 11 people, then there has to be, like, you distribute the mangoes, that there has to be at least one person who will not get mangoes, right. So that mango is not mapped to anybody. So it's something like that. So the point is this, the proof is going to be this: we have seen that the set of all languages is uncountable. We will say that the set of all Turing machines is countable, right? But each Turing machine recognizes only one language, right? So there is exactly a set of strings that Turing machine accepts, right? So given a Turing machine, there is a language corresponding to it, the language is recognized by it. But there are only countably many Turing machines, but there are uncountably many languages, which means uncountable is far more than countable. So which means there are many languages, not just one, there are many languages that are not recognized by Turing machines. So this shows that there are languages that are not Turing recognizable, which means there are languages that are not decidable, because being decidable is first requires you to be Turing recognizable, right. So let's go over the proof very quickly. Anyway, I have told the high level picture, right. So consider a set of all Turing machines, right. So given any Turing machine, as we saw in the previous week or in the last lecture of chapter 3, any Turing machine has an encoding, right. So given a Turing machine, we can list down all the alphabet, list down all the rules in zeros and ones, right, and it gives a finite length string, right. So suppose we encode the Turing machine into a finitely long string, finite string, okay, because it has a fixed set of rules, fixed set of alphabet, everything is fixed. So the description is going to be finite, right. Now since the description is going to be finite, every Turing machine has a finitely long description. Over any alphabet sigma, we have the set of all finitely long strings is actually sigma star. So all the encoding of all the Turing machines is going to be a member of sigma star. We know sigma star is countable. So the set of all Turing machines is also countable, right. right? So it is not necessary that all the strings correspond to, all the finite strings correspond to encodings, but whatever are the encodings are finitely long strings. So it is going to be a subset of sigma star. So since sigma star is countable, the set of all Turing machines is also going to be countable. But each Turing machine recognizes exactly one language. So give me a Turing machine, there will be some strings that it accepts, some strings that it does not accept. So what I am saying is that every Turing machine M recognizes exactly one language, right? So this means that there are languages, but we know that the set of all languages is uncountable. That's what we saw just now, right? Just before coming here. So set of all languages is uncountable, and set of all Turing machines is countable. So it's like this, and the set of all uncountable set is much bigger than countable set, right? So this is set of all Turing machines. This is set of all languages. Right, which we call L. So this is uncountable. This is countable. So you cannot have a bijection. In fact, there are the even though I drew it kind of similar size, this is much bigger. This is much bigger. So which means there are many languages. In fact, there are many there are a huge number of languages. In fact, most of the languages will be not recognizable by Turing machines, right? So given any Turing machine, it corresponds to only one language, and hence you can have a mapping from the set of all Turing machines to set of all languages, but many languages will not be. It will not be bijection. So many languages will not have Turing machines corresponding to it, which is the same as saying that there are many languages for which there is no Turing machine that recognizes it. This means that there are languages that are not Turing recognizable, right? So if L is decidable, or L is decidable implies that L is Turing recognizable, right? So for a language to be decidable, we want it to be recognizable and halt on every input. So if it is decidable, it's certainly recognizable. This means that, so since there are languages that are not Turing recognizable, that means there are languages that are not decidable. This means there are languages that are not decidable. So, and that completes all the things that I want to say in this lecture number 36. So, right. So what we said is that the set of all infinite binary strings is uncountable. Set of all finitely long strings over any alphabet is countable. Set of all languages is uncountable, and because of a mapping between the set of all infinitely long binary strings. But the set of all Turing machines is countable. But every Turing machine corresponds to a language. But the number of languages is uncountable, which means there are way more languages than the set of Turing machines, which means there are many languages that are not recognized by any Turing machine, which means there are languages that are not Turing recognizable, which means there are languages that are not decidable, right? So it's an interesting way of proving it, right? So we said that there are languages that are not decidable or languages that are not Turing recognizable, but the proof did not produce any specific language. It just said that there are such languages just by this counting or bijection argument. You have this set that is countable, this set that is uncountable. So there are way more elements in the uncountable set as compared to the countable set. So you cannot have a mapping. So this means there are languages that are not Turing recognizable, hence there are languages that are not decidable, right? So we saw that B, the set of all infinitely long binary strings, is uncountable. Set of all finite strings over a language, over an alphabet, is countable. Set of all languages is uncountable. Set of all Turing machines is countable, and hence there are languages that are not Turing recognizable, and hence there are languages that are not decidable. And that completes what I had to say in this lecture number 36. In the next lecture, we have built all these theories. In the next lecture, we will actually take a specific language, which is ATM, and then show that this language is undecidable, right? So far the argument is kind of based on this set is small, this set is big, so there are elements in the big set that cannot be mapped to the small sets, right? So now we will actually take a specific language and show that it is undecidable, meaning no Turing machine can be a decider for this language, right? So that we will see in the next lecture. So see you there. Thank you.